Um, in case you haven't done it last time, please fill out the sign-up form. It contains all your basic information, like which year you're from, your major, etc. All right. Okay. Thanks everyone for coming to the lecture today under such a cold weather. Can I just ask before we start, is this like a normal code day or is one of the code day in a number? Normal? Okay, I see how it is. Okay, cool. Yeah, just in case you did not fill this out or this is your first lecture, please scan this QR code and then fill out the form. All right. Okay, let's get started. So today we're going to do some introductions on the instruction set architecture, or ISA. Many of you have taken 370 before, as you should, and then this lecture might feel quite familiar to you. That's totally okay. Just sit this through and try to be more active on Piazza when other classmates trying to ask any questions. Do not have wait to us to reply any of the questions. Some quick announcement first around the logistics. Again, the class website. We are getting emails from folks who are asking for Canvas access. We will not be using Canvas, unfortunately, for this semester. It will be reconsidered for next semester. So as for now, we will be using our own class website, as well as Piazza and Grayscope. So as long as you have fully access to all those, you should good to go. And for the homework assignment, lectures, slides, etc. on the website, make sure you click on those links, use your UMISH email address instead of your personal Gmail so that you have the proper access. And Piazza, as usual, is the first place to ask questions and also looks for answer. Other related to the assignment, we have the homework 1 due this Friday, and this week will be where we start our labs. So normally the pre-labs are due before the lab section starts. This week's will be due in lab, and also the post labs will be due after lab, as the name indicates. But this is only for this week. Normally the pre-lab will be due before your lab session starts. And on the office hour, we got notified by you guys in the class that the previous proposed time is actually in conflict with one of our lab sections. I'm very sorry about that. So I will be switching it to still Wednesday, because I think it's good to have the office hours on non-lecture days, so that in case you have something in between or just want to cover more days of the week for the class. So it would be Wednesday, 11 a.m. to 12 p.m. Does that sound good to you guys? Any concerns for that time? Okay, great. So, but that will be starting next week, unfortunately. This week I will still have to do 3 to 4 p.m. On Wednesday, because there's a 4-hour PC meeting I have to be in tomorrow morning. And the location will be in the EECS building, 3217 for now, but for the next month or so. That's my temporary office, and then I'll be moving to a more permanent office in March, hopefully. And during the open lab hours on the lab calendar, not sure you guys see the class website yet, so we updated the labs schedule with the lab sessions, also the open labs. Basically, those are the times you can just come pop by and do your lab or asking questions regarding homework or anything to the TA or GSI or Matt and James in it. Cool. Okay, yeah. Before we jump into the ISA, let me give you some components of the day. So basically, connectors. This might or might not feel familiar to you guys, but the connectors are actually quite important. So embedded systems, as we discussed before, are quite dynamic, and it would be quite different from the previous lectures you took, which are self-contained. In our class, it's going to be much more open-ended, especially when the project phase coming in. You will be interactive with all kinds of different components, and then chances are you have to connect them to your system or to your board. And they're going to have various different type of connectors. And we chose this to be the first one to show you guys, kind of as also a safety requirement, because some of the components do draw a significant amount of current. So if you are doing those type of components, make sure you pick the correct connectors. And normally for those components, they also have those what they call foolproof or arrow-proof design. So for example, these type of battery connectors, this is typically used in Leopard battery, etc. They can only be plugged in one direction. So if you're trying to connect it, wrongly, it will not allow you to do that. So yeah, also just a future reference when you design your future systems or product, always keep in mind that there is a certain percentage of the users that are going to be, very challenging or very exploratory. They're going to try things that your products are not intended to be tried. So keep that in mind in the future. Always design these, foolproof designs, or you can call those Morpheus law for general users, etc. And just in case you want to learn more, there's a YouTube link for different various type of connectors. Most of these are mechanically connected. Over the past 100 years, we have figured out that there are these type of mechanical connected methods that work quite well for different amount of current you're trying to drive or different types of the voltage you're applying. A quick review from the last lecture. So we did the class overview and then show you a little bit what is the embedded systems and how we get there and where we're going. And then we give you some high-level ideas of the ARM system architecture, as well as a quick intro to the GPIOs. So the goal for the next 2 weeks or so is going to be understand how the code, or in our case, the instruction architecture, ISA, memory, as well as the register, how they work together, and how the microcontroller unit MCUs interact with outside of the system. So basically, interact with the physical world via the MMIO, memory mapped in and out system. So for today's lecture, this is a quick layout. So I'm gonna give you a overview about some background in ARM architecture, and then we jump into the instruction set architecture, ISAs, around memory, register, data width, etc. And then the instruction specifics ones, we're going to talk about mainly some of the instruction encodings, some of the logic instructions, and then move, load, store, as well as branching, etc. So these part of the content should be more or less familiar with you if you took 370. So yeah, I wouldn't work too much. And then we're going to have some quick index problem if we have time. We'll see. Cool. The ARM architecture. Basically, there are about 160 billion ARM chips shipped in our world. And how do they actually make a business model out of it? So keep in mind that the ARM is a fabless semiconductor company. Does anyone of you know what fabless means in this case? Oops. The fabless. So basically, how is the ARM make a business model? How are they making money? Yes?
They don't actually fabricate them, they just create the architecture design? That is, yeah, more than correct. I noticed that I accidentally popped this up, but I'm sure
you guys have noted it by the name of the fabless. So basically, it's basically creates the chip architectures and creates the instruction set, the command to go with it, as well as so basically, and then they wrap it up as like IPs, intellectual properties, and then license that to different companies who does actually make chips. For example, of those big companies, a lot of them you will be very familiar with: Apple, Samsung, Texas Instruments. So, does anyone of you have some thoughts on why they're not making their own, like those companies like Apple or Texas Instruments, etc., Samsung, why they don't make their own architecture design? Any thoughts? Yes.
So it's just cheaper to get it from a company that's able to make it really well.
Yeah, cost effectiveness, definitely, that's one of them. And any other additions to the, yes?
A lot of work and you need specialized people for that. Don't need for anything else.
That's a very good point. It's very hard, and it's very hard to make it right. So those like small bugs that can be popping up everywhere. And any other thoughts on this? Yes.
The integration with other devices.
Yes, very, very good point. Basically, it's easier to be like generalized and also compatible with other devices made by different manufacturers. So yeah, also it's easier for programmers. So imagine you learn like one type of language and then with a certain compiler, and then you can run your code on various different chips that as long as it runs on the same architecture, chip architecture. So that's also how we get to make, I guess, CS or EECS such a booming industry. It's worth noticing that some of these companies do make a lot of modifications to the ARM architecture. For example, like Apple, when they do their A chips, they actually make a lot of custom modifications, but still it's based on the same ARM architecture, so that can be used by, I guess, majority of the programmers and also compatible with most of the a lot of those peripheral devices out there. Cool. So of course, there's not possible to have one set of chip design for everything. The ARM Cortex actually make different families. The family A, R stands for real time, as well as M. The A is basically you can imagine like anything that with a screen, and also like more general purpose computing. Though those are most likely have like a chip inside. For example, Apple's chip was based on their Cortex A family. The R family, it's emphasized on the real-time responses, so they usually be optimized usually for like very high reliability required applications, such as like transportations, etc. And then there are the M family, which is what we taught in our class, where we were teaching in our class, the microcontroller. It basically have like low power, and it's more cost sensitive, and also more everywhere, you can see. This is like a more detailed layout. So basically, when we talk about like the chip architectures and instruction sets, there are actually two separate things. First is the architecture. It's more like hardware, and the instruction set is more software. Basically, it's kind of like a agreement between the programmer and the chip. When you import this type of command, the chip will do these. And you will notice that there are a lot of overlapping. So in case in the future you run into like a new chip that you want to know how is it working underneath, make sure you have both of them line up, the chip architecture and the instruction set. So for our course, we're using the V7 and the Thumbs2 instruction set. So we talked a little bit about this, but what is exactly an instruction set architecture, or ISA? It's basically an abstract model of a computer. It kind of like, let me just pop it out. Yeah, it basically is like an agreement between the programmer and the hardware designers. Use these instructions, and the hardware is going to do exactly these following things. And the ISA defines the some of the instructions, for example, like add, subtract, move, load, store, as well as like the data types. Are we doing with a word? How many bits? Is it signed, unsigned? And then it handles the data storage. Like, is it going to a register or is it going to the memory? And address and the data flow control. So far, so good? All right. And yeah, we have a different types of, we have a different size of the ISA. There are like 16-bit ISAs or 32-bit. So for our SUM2, actually it's a mixture of 16-bit and 22-bit. And usually when we have like 22 bits of the instructions, it's more expressive. You can do more things with one command, or load more data or interact with more memory addresses. But with the 16, it's optimized for like code size. And if you have, say, very limited memory space you're working around with, etc. And the SUM2 claims to be having the good part from the both. So we don't really know if it's a marketing thing or it's actually like that, but we would just take the word from ARM Cortex. And this is like a very general like overview of the SUM2 instruction set. It basically supports different types of instructions as well as like the backward support. So not only supporting the SUM2, it also goes way back to previous versions, which is like a pretty general design rule for a lot of the hardware, especially on the chip level, because you want to keep things running until, I guess, finally you have to retire them, but hopefully you can keep them alive for a while. Okay, so a chip architecture defines basically how the instruction sets to be processed at the hardware level. And our class will be focused on like the V7M architecture, and which is where the hardware piece that's the instruction set is going to be running on. And you can consider the following example. The Cortex A8 is a variant of the Cortex V7A architecture and have 13 stage pipeline core, while the M4 is a variant of the V7 again, but M architecture and have 3-stage pipeline core. So, and they can basically both run SUM2 instructions, just each architecture chose to implement it in different ways. All right, let's go to the word sizes that we're working with. So basically, do you guys have any ideas which like technological trends are causing the shift from previous 16-bit to the 32-bit microprocessor architectures? Any thoughts? Yes. That's a very good point. I think this trend happened before the machine learning period, but that's a good point. Yes. Yes, exactly. So with basic, that's one of the very, I guess, the main driven force. Basically, with more bits, you're able to interact with more memory space, and then improved with, and then the program get more complicated, and then more memory space needed. So essentially, they shifted towards the 32 bits in the end. And why, even with those things in mind, why are they still keeping the 16-bit and then trying to like make a hybrid version out of it? Think about like, yeah, okay. Yes, it is easier to execute and probably going to be resulting like faster time. Any other points that might, yeah.
A lot of signal processing applications only require 16 bits. So unless you have large inputs, you don't need 32.
Yes, I would add a little bit to your point. Exactly. So basically, a lot of the process only needs 16 bits, and then because the embedded system have always have this trade-off between like cost and power and efficiency, so it make more sense for those if we keep those 16-bit instructions to not only make it a little bit faster, but also trying to save more energy and more cost-effective. Cool. But all the registers are 32-bit, and they just can't determine whether use the 16-bit or use the entire 32 bits for that one instruction. Yep. These will be posted online, so don't worry too much about this. All right, let's move on to the memories. Okay, this is from the last lecture. This is like a very general overview of the Cortex-M4 architecture. And remember we talked about like all the buses are 32 bits, right? And as well as all the registers. So for this lecture, we're only gonna care about like core and memory, how are they interact with each other. So, and for the memory, for the simplification, we just call it like a unified memory. Basically refers like memory architecture where like a CPU and CPU share like a single pool of memory instead of having separate memory spaces like dedicated spaces, like more complicated general use computers. Basically just consider all the memories the same in this lecture for now. And about the memory organization, so how exactly are those memory being managed inside of our core or inside of our chip? By 32 bits, so basically we're gonna have, in theory, about 4 gigabytes of RAM, but in the end, they actually, oops. Yeah, so, but in the end, they don't actually always implement all those. So for example, the ones we have allocates only like 500 megabytes of the space. So any guesses on why they do that? Although we have capacity to interact with 4 gigabytes of memory, but they only allocated or only put in 500 megabytes in the hardware. Yes?
Is it just faster than only have certain cores per die, like that's what all
I think it is slightly faster, but in terms of like each instruction running time, it should be smaller than the clock time. So that would not be like the main factors in this case. Basically, the address, the time it takes to find the address in the memory would be like less than most of the clock. Yes, but that's a good point. Yes.
Is it because more memory is allocated to other types of storage systems? Like maybe more memory can be RAM and some other memories would go to allocated cache or whatever.
I see. I think those sometimes happens in like more general purpose computing in the microcontroller systems here. It's usually they actually did not implement it on the hardware, so to speak. Yes.
Would more memory cause slower access time?
That's I think a little bit similar to previous points, but yes, it does. But in the end, that amount of time would not going to be majorly affect how long the program execute because of the clock time the microcontroller tends to be slower than it's going to be finished all that in one step basically. But yeah, I think we should, when we design like the embedded system, we should always keep something in mind. It's basically the trade-off between the performance and cost. I hate to break this out to you guys, but it's also for the cost-effective like considerations. And in fact, they usually, even for the same type of MCUs out there, they give you different choices on how many SRAM, for example, you want to have on the chip, different versions, so that you can have exactly the amount of computation power and the storage you needed for exactly your application. For example, I'm not sure if you guys work with like ESP32 modules, like a very cool multi-core Wi-Fi BLE integrated microcontroller. So yeah, basically they sell like 4 megabytes, 16 megabytes, 32 megabytes, etc. at slightly different costs. So for you to choose from. Okay. Yeah, so basically we're going to treat both the flash and the SRAM as one unified memory for the lecture. And I know that the access time is slightly different, but in our course, at least for now, let's just consider they're pretty much the same for now. And the memory addressing. So each memory location, despite how many actual memories hardware they're putting there, it's still going to be a 32-bit address. And each of the memory location holds basically a byte instead of. But things we're considering like a 32-bit architecture, sometimes it's easier to think of these as like 4 of them at a time, so basically 4 bytes at a time. So yeah, you can think of, or you should think of the memory as being like 32 byte wide as well, just so that it's easier to work with in the later instruction sets. And you can always, I think for the most of the either homework or the exams, like the address increments by 4 is going to be what most commonly used. There are some other cases for like half access or move wide, move top, etc. We will cover in a little bit. But yeah, for now, just think of them as like 32-bit wide for the memory data as well, and then increment the address by 4 every time. Does this part, like everyone gets this so far, right? Any questions? Okay, cool. And we have the big Indian versus little Indian. I'm not sure if you should probably be familiar with these. Basically, it's the way how the data is stored, like the least significant bit versus the most significant bit, like where we put them inside of the register or memory. So for our course, we're going to use the little Indian system. Although, interestingly, our chip can work with both. You just have to specify, are you doing like a little Indian or doing a big Indian inside of your instruction. And as we briefly talked, as I briefly mentioned before, the registers, they're all 32 bits wide, and then we have 16 of those registers for the code. The first 13 of them are the general purpose registers, and then from the 13 to 15 are basically some other specified used registers. For example, a stack pointer, link register, or like program counter, basically telling you where are you right now and what's the next address you're going to inside of the instruction. We also have some special registers. So for example, on the right, they're also basically just 32 bits. And then you will likely interact with them in like branching or like some other code controls. But for now, I think the on the left side is more important. Okay. All right. So how is the load code and data into memory works? Let's see. Let's break it down to different parts. So basically, we have the data initialized, and then the data goes to the stack, and then goes to the SRAM. This is like a, and then when you have like a initialized, it also got pushed to the stack and then goes to the memory. We're gonna do like overram for now, and when we access the for loops, etc., it will goes to the flash memory, and then loop is through every time. It just stored it in the memory, and then jump to the next instructions based on where the instruction pointer, like the control pointers is pointing for the next instruction. we have any questions so far? These are, I'm going a little bit fast because I think most of these stuff should be already covered in the 370, but we're gonna have to reiterate on it so that for the next part of the lecture, you guys are much more comfortable with the move instructions, load and store, etc. All good? Okay, cool. All right, next we're gonna go into the actual instructions. So basically, review from how the instruction works. You have the code, and then it got encoded, instruction encoding, and then it goes to the machine code. These are some of the instructions here. Move S, basically the move immediate with the states update. It updates the condition flags, if you have any, for like branching purposes. And the hashtag 10 defines an immediate. So basically what's happening here is you have a number 10, and then you put that into the register 0. And this is how the machine code looks like. So basically the first one is the move S, basically the machine code for that 001, and then the next will be which register is put it in, and then in the end, it's basically number 10 that's going to be put into that register. We're going to have like cheat sheet for these stuff for either your homework or like exams, so that all you have to do is look up for the right type of instructions to write if you want to decoding it into machine code. The important things here is basically know which type of instructions you're trying to do, and then kept tracking of where it's the address of the memories and where you are inside of the program. And similarly, if we do like the basically moves the 0 into the register 1, and then it goes to the same function here. Notice that they put inside of the same memory address here. Oh, what's happening? Okay. Any ideas why here? Why they're putting into the same? When I say same, I mean it's like 4 byte, basically. Why are they in the same 4 byte memory location here? Yes? Yes, exactly. So remembering like the hybrid model we mentioned in the Cortex, the thumb 2 instructions. So basically you can specify it, whether it's a 32-bit instruction or 16-bit instruction. And depends on how that's sorted out, you will be able to store accordingly, except the memory. And then you will have operations to be able to access either the top part or the bottom part of the memory. Just make sure you keep track of the address. And then it's basically the program counter, which is one of the special registers we talked about, the R15, that holds the memory address of the next instructions to be fetched from the memory. And always it's do the 32 bits from the memory. So whether it's 32-bit instruction or 16-bit instructions, they always got fetched in like a 32-bit way, and then they got executed. So how do they actually work? In a 32-bit, it's pretty standard, basically like a 3-stage pipeline goes through, and for the 16-bit, it's actually a little bit trickier, but still, you can probably imagine this. Basically, it have like one extra cycle to wait for the second part of the 16-bit, and then basically adding one stage to it, and then do the and then execute the instruction. So I have a question for you. When the core fetches the next instruction, how does it know if it's one 32-bit instructions or it's actually two 16-bit instructions? Any thoughts on this? Let's talk to your neighbors for like 30 seconds or 1 minute, and then we can discuss together. Or if you were to design it, how would you design this? Alrighty. Okay. Anyone wants to share what's your thought? Feel free to share either what you think, how they did it, or how would you do it. Both of those are okay.
Yeah, my friend said that the first bit might just...
Your friend said that?
Yeah, he said the first bit might just, of the, like, because there's 5 bits for the output.
Mhm.
The first one might just be whether it's 30-bit or 216-bit instruction.
That's a very good strategy, but basically using specific bits inside of the instructions to determine whether this is a 32 or. So how would you, which location you will put it? Say we have like a 32-bit data coming, which index or what's the rough area you will put it in? Top half or bottom half, etc.
The beginning,
The beginning.
because you might need registers or, registers or like offset values at the like end, I guess.
Sounds good. Yeah, that's very reasonable, and probably how they did it as well. Any other thoughts on how would you do this if you were to design this? All right, we only have 32 bits to work with, so I don't blame you. It's a little bit complicated than that. It's instead of 1 bit, they actually look at 5 bits to determine whether it's a first half of a word of the 32-bit instruction or if it's a 16-bit instruction. And so it's a little bit combination of logic that decodes, first 5 bits and then, decide which ones to run. Again, all these answers will be posted online, so don't worry if you can't write them down just yet. So let's do another quick encoding exercise. So for example, for this instruction, and on the right, we have 2 different types of encodings, T1 and T2. You can see their so instruction size, 16-bit and 32-bit, and then these are basically what's the each index of the instruction set is corresponding to. So if we have this move as R3 and 15 immediate, which type of decoding would you run this on? T1 or T2, like 16-bit or 32-bit? Any thoughts? Oh, so basically, this is the instruction we have, right? Would you put it inside of a 16-bit instruction or into a 32-bit, basically? And then these are the how inside of that piece of instructions, how each index was assigned based on the index. Yes. Mm-hmm. That's a very good point, and you're probably right as well. So it's totally enough to hold a 15 instead of a 16-bit instructions. And how about this one? Yes?
You would need to do the T2 because you only have 3 bits in the T1 encoding, but since R9, you need more than 3 bits.
That's very much correct, yes. Notice that inside of the, basically on the T1, you see like the RD, it's only have 3 bits. So that if we are trying to use the register 9, then we have to use more bits to represent which register is going into. How about this one? Okay, I'm just just going to go ahead and say this. It's going to be, T2 because of the data itself is actually exceeding the amount of the bits that's assigned for the T1, which is only 8-bit. And this one, it requires more than that. So, the actual questions here. How does the ISA make a distinction between low and high processor registers? And how do they use, does that make a difference, whether they're using the 16-bit or 32-bit? It's very much, did I say the question correctly, like clearly? It's basically, it's very much related to the previous exercise we did. So which are the things that they need to be considering? And then what's the thing to distinguish them made if they're using different type of registers? And feel free to chat with your neighbors on this one. Oh, yeah. Let me show you. Yeah. For the reference, this was the, yeah. T2? Oh, it's actually combination. So there are 8 here, 3 here, and then the first one is here. It's a little bit jumpy for whatever reasons. I'm sure they run some kind of optimizations and then finally decide this was the correct index to go. But that's for the data part. For this question, it's more like, what's the difference, or why do they make a distinguish between the low and high registers? So this will be more focused on like where this and that, rather than the data. All right, do we have any thoughts that I want to share with the class? Anyone? Yes?
It might make more sense to put like smaller numbers in the low registers and higher numbers in the high registers. Like, for example, with the last slide, with like 416 and whatever the bottom was, if you swap 416 and 15, you only have to use T2 once, because you're already going into like a higher register, so you might as well put a higher number in there and keep it like to a minimum.
I see. Yeah, that's a valid point where, well, which way, like whether you should choose like 16-bit versus 32-bit. So yeah, let me. So for this one specifically, inside of the core, it's being separated or internally labeled as low registers, meaning the index of the register are from 0 to 7, and also high registers basically from that point to 12, and the remaining 3 are the special ones. But so why do the 16-bit and 32-bit instruction impacts how the instruction will use these registers, rather than how the data that's being loaded that impacts how they're going to use the registers? Yes?
For 16-bit instruction, it doesn't have to have space to even encode R9 at all. So it's really unaccessible at all.
Yes, exactly. Remember from the previous example here, that when we do the R9 here, we have to use the 32-bit. and then that will goes to, in this case, the higher registers. So basically, to put it short, the 16-bit instructions have a limited number of bits that can be used to represent the registers in the previous case, and actually in real life, 3 bits, so that they can use essentially only the lower indexed registers, where the 32 bits, they can use and access all the registers. Good, yes?
Question about the so Genesis switched to the different so it has a signal one for let's make it one.
Yes, so remember previously, so there's a very specific index from 15 to 10. Basically, look at that, and then if that's a certain pattern, then that means it's a 16-bit instruction, or is it a 32-bit instruction? Yeah, from the previous slides, basically the labels. Yes.
So can you read 2 instructions into the register at once if they're both equal?
Yes, and that's how it's being done. So when you load the instructions, always 32 bits. If it's 2 16-bit instructions together, we load 2 instructions together. And if it's one, regardless of the 16-bit or 32-bit, it's always loading 32 bits inside of that. Yeah. Cool. Good? Yes?
Well, then if you have a 16, does that mean 16-bit instructions have to come in pairs? Because what if you want to do a 16-bit, then a 32-bit, then a 16-bit? Do you just fill it in with zeros?
I think they have different ways of doing it. They might do some filling zeros, but I also think usually they have some other inside of the compiler. They will allocate them more smartly for the saving memory. But I think some of them do fill with zeros if it comes down to that. Yeah. All right. So these are some. These are some type of assembly instructions that's supported, and among those, we're gonna just basically look at them one by one. Some of them go faster, some of them go slower. Let me know if you want more information on any of them. So first is the logic instructions. So yeah, again, this is how the menu looks like, and we will provide these cheat sheets to you during class and also homework. So you will know exactly what's these code means and what it does for you. And these are like the commonly used operations: add, subtract, multiply, etc. As well as, there's a S bit, if you can see highlighted. So those are basically for updating the ALU flags. This is one of the special registers that we mentioned previously that will be keep updating. Usually for like the branching purpose, you have like if statement or some other while, branching, etc. Okay. And give you another example, basically we also have like a conditional flag for like a carry out bit. This is also one of the special registers. And this is for the time if we have some even larger amount of data we want to process, even the 32-bit instruction cannot hold it, then we have like 2 instructions to do that, and then basically put them together inside of the memory. And how exactly that works, we can take the example here. Basically, for the addition, it will load them into the first load into the lower level of the register, and then load it to the higher level instructions, and then add them together in like a first add the lower 32 bits, and then if there is a carryover bit, and then they updated that. So that's why here has an S there to update the carryover bits inside of the ALU, and then it does the add on the higher 32 bits, so that we can essentially operating more bits than 32 bits additions. Okay. These are just some of the flags that we will be using, as flag is one of the, I guess, go-to flags you have inside of your move, store, or etc. Good. Okay, and also the instructions set supports bitwise logic. These are basically, AND gate, NOR gate, and it does these in like a bit-to-bit purpose. Here is like an example here. It's like a OR operation. Basically, those are some examples and how the output will look like if we do this operation. This is essentially like a OR gate. Okay, and why do we need these bitwise comparisons? Can you guys think of anything that can be useful for these type of operations other than traditional add, subtract inside of the LU? Yes.
If you want to set specific dates without changing anything else, you can use OR and.
Yes. So yeah, exactly, and I will add a little bit to that. So usually inside of the embedded system, sometimes you have this one bit that's connecting to some other devices as like a switch, or that bit was connected to a GPIO pin. So instead of reading through the entire data, all you want to know is what this system needs to do at this step with that one pin, for example. Then it's much faster to do this with like a bitwise instructions. So essentially, it's like a mask. You just do this, and then it returns you the results, and you don't care about other bits. And you also, more importantly, do not modify other bits as well. Yeah, this is like an example of how a mask will work. Basically, you only look at the the lower 4 bits of this one. So far, all good? No questions on the bitwise operations? All right, cool. Oh, you guys took the 370 really well. Yeah, next we're gonna move to the move, load, and store instructions. So basically, these are like different ways of moving data between registers. One of them you might not be very familiar with, the MBN, basically move out instructions. It basically takes like a value, performs a bitwise NOT operation, and store the result inside of the register. But yeah, these are just some different ways to interact with the registers, between registers. And then this is the example of moving immediate number to registers. And then we have, additional to like the normal move, we also have the move wide and the move top. So this can be a little confusing, but basically is that when you do the move wide, it does not, it basically wipes out the higher bit and then load the data to the lower bit. So you kind of have like a cleaned register. And the move top here is it basically loads the data to the top bit and then leave the lower bit as it is, as before. So imagine you have to move, say you can't take like 32-bit of data all at once, you don't have enough space, and then you have this instruction here to load 2 of the data inside of the 1 register. What's important here is basically the order of you doing this. You have almost always make sure you do the move wide first and then the move top. Otherwise, you're going to mess up the data inside. Any questions so far? Or is all good? Okay, cool. Yeah, just keep in mind some of the instructions, the order, how they execute it or how you write it up matters on how you're gonna end up with the memory or register, the values in the register. And let's also look at some example of the load. So this is basically like a vanilla version of the load. It goes to the memory, and then the bracket meaning the memory location, and it loads into the register R3. And there are, of course, different versions of the load and store, and you will see some of them, these are highlighted here, some of them have like H or half as their, indicating, so basically they only load half of the memory, of that memory location, the data there, as well as B stands for like byte, it only loads a byte. So it just depends on, which type, what is the address, what's the data you're trying to load from the address, and how big the data is. These are the instructions you need. Yeah, exactly. And can you think of why there is not like a store H or like store have instruction to be included inside of the current instruction set? Any good reasons for that? Talk to your neighbors, and why we only have these for load rather than for store? The options of storing into some, yeah. All right. Any thoughts so far? Anyone want to share? Anyone? Yes. Yes, that's one good. Yes, that is one of the reasons. Yeah, you have different type of memory. Some prefix are needed for for example, like signed, unsigned, so that it might not be enough space to store that data. Any other reasons? That's one of the reasons actually. Any other reasons as well? Yes.
I don't get it, because if you have if you have 32 bits of data,
Mm-hmm.
and you sign and extend to 32 bits, that's the size of your register. So why wouldn't you be able to store that somewhere?
You will be able to store that somewhere. The reason they don't allow you to store half in this case is that because the memories doesn't actually know which type of the data it is. Is it a signed integer, or is it a string, or is it unsigned integer? So in order to protect that, they just cut that off and do not to make sure they have the prefix inside of each of the slots. That's one of the reasons. Any other thoughts? Yes.
Whatever produces the data should worry about the upper bit.
Yes, that's also one of the reasons. Kind of, yes. Yes.
The whole point of the half storage that you're storing, like a half word. So if you're gonna extend that, then it doesn't make any sense. You like extend the half word and store more than a half word. If the instruction says that you're gonna store a half word, that makes sense.
I might have to think a little bit more on that, but it's. But I guess it kind of makes sense. I guess for this one is like even if we have a data struct like a small number that could fit in just half of space, but why we're not even do that, or like why are we not allowing such instruction exist? I would just add one more point to this. It's basically also trying to like protect memory, so we don't want to like crop any of the other memories, so that we kind of like make sure each of these are the same same size, so that we don't mess it up, so that we know exactly at which address, and then we should load, just trying to keep the memory safe and not being mess it up. Okay, so another thing you probably interacted with a little bit more is with the load and store is these addressing modes. So basically, let's take a look example of this. This is just a normal load from the address R0 and then put it into the register R1. We go to that address, pick the number, pick data, and then put it into the register 1. And we picked the entire 4 bytes as we said it before. So basically 32-bit at a time, and then load that into the register 1. Another thing we can do here is offsetting address. So basically, we add another 4 here. So after we load the, basically we offset the address on the fly, and then find the offsetted address, which in this case, we added 4 bytes to it, and it finds that address, and then load the whole thing 4 bytes, and then put it inside of register 1. These are pretty common in like, loops, etc. But in this case, the register 0 number here still keep the same. And in the next, we also have pre-indexed addressing. Basically what this does is it changes the R0 immediately, and then do the load. And for this version, the R0, the value in the R0 is changed permanently. And then it goes to the address, and then it loads the same data to the register 1. So for the register 1, the end result is the same, but the R0 compared to the previous one is being updated in this instruction. Yes? Oh, this one? Oh, so basically, this is a load. And then the first is which register you put this data in, and the second is basically what's the address you're looking inside of the memory. So the load command basically takes an address and then trying to find the data and load that into the designated register. And just to make things a little bit more confusing, there's also a post-indexed addressing. So basically, oops, sorry. Yep. Okay, here we go. So it's a little bit similar to previously, but the difference is in the order. Remember previously in the move, the order also matters. In this case, it will basically find that address first, load the data, which is 1 to 8, and then increase it after that. Increase the register 0 after that. Keep those two in mind, basically. When you have the bang sign, it's immediate, and then if you have none of that, it's after. Good? Okay. These are just like different types that are used for various for loops and to improve the code efficiency, etc. So a quick summary here. This will be like a good chart to have. Basically, all different types of the index format. You have like no index in the banana version. It's basically load from the memory address and then put it in the register, and nothing changes except for the designation register. And then pre-index, and then the pre-index with update with the bang sign, or the post-index. Basically, you load the address and then increase the index of the register after you load the data. So, question here. For like a load instruction, what's the largest possible offset if we're doing like the offset addressing that can be achieved with an immediate? Immediate is the bracket with the, yes?
I think it would just be like all 12 bits would be 1, so it would be 2 to the power 12 minus.
That is exactly the answer. Yeah, good for you. So this is the largest amount we can shift during any of those load or store instructions. So far, so good? Okay, we're going to move to the next part, which is basically the flow control and branching. This part is pretty straightforward. So branching or B labels here are, if you just see like a B, it's basically unconditional branches. Whenever you run into that, you go to whatever that instruction tells you to do. And we also have a few like condition ones, BL, a branch with link, or like with link and exchange, etc. These things will always be like put inside of a instruction menu. You can always find those either doing homework or during the exam. And here are some of the conditional codes that's being used. For example, like, okay, I'm not sure what's happening. Okay, so basically, equal, not equal, carry bit, etc. All those flags that can be used inside of the processor. And these conditional codes can be added with the other instructions too, even with like say load. And these are just some examples of that, how they work together. And you don't have to go all into details, just as long as you know which type of the instruction you're trying to perform, and then trying to look for the correct one inside of the data sheet. And some other like comparison instructions, compare these two registers or compare negative, etc. Any questions on the branching or? Okay, sounds good. And let's do some practice. So I think based on previous lectures, based on previous years, it's usually the load store or like move. Well, usually load and store causes most of the questions. So let's go through some example together. Let's assume X here is a 32-bit integer that's stored in memory, and this is the C statement that puts in, and these will be essentially the assembly code that's being constructed from being decoded from the C statement. And with that, this is how the current register and the memory looks like. So first is the PC, which is the program counter, and it tells you what's the address of the instruction we're trying to go to. And that address links to that, and that 32-bit here is corresponding to load R101. You don't have to memorize, of course, but basically on that you will find on the cheat sheet, which bits corresponding to which command, and then you can just decode that yourself from the machine code to what's the assembly instructions. So once we have that, we have the, we're just trying to find the location, like the address in the memory, which is 20000. And then we find the data that's stored in that location, which is 2. And then we load that into the register 1. Yes?
So the X inside it, or I mean the bits inside it, like there are two memory locations.
Wait, which one?
You see when you're pressing the instruction,
Oh,
two of them have the same address. So,
good catch. Sorry, I'll update that. Okay. The previous one is wrong. So yeah, that's. And then the next instruction, basically, it will goes to the next instruction, which is 4 bytes ahead. If there's no jumping or branching, that's basically the default, how the program counter is going to go, the next 4 bytes of instruction. Oh, actually, sorry, my bad. The previous one is actually, I think that was actually correct because we're doing like a loop thing, branching thing, but we will see in later. So in this one, it's basically a decoded into the add instruction. We add 1 to the register 1. So what it's going to do is the ALU pops in and then add 1 to the previously stored 2 and make it 3. The add command, all good? Okay. And then we're going to store it to a different location. This, again, the program counter counted up, and then it tells you to store the values inside of the register 0 to the R1. So that's being updated, oops, to the R1. All good? Any questions so far? Okay, cool, perfect. So before the class ends today, let's just do one more group exercise. You will work with your neighbors together, and then, yes?
So, good question. So, say it was right and it was a loop. How would the fetch instruction know which memory address we grab for this?
Sorry, can you say it one more time?
So you said they have the same addresses.
Oh, yeah, sorry, my bad. You're actually right. I will update that in the slides. Sorry for confusing. Yes. Okay, so the group exercise. So basically, what this would be asking you is to, this is essentially, you will probably see like a loop. Basically, you have jump to the jump, and then do it over and over again. And then we would like you to work on what's the memory going to look like after or during each of these loops. Like, for example, the cycle 1, how the memory going to look like, or the cycle 2, how the memory going to look like, etc. I think we can just do the first 2 loops. That should probably give a pretty good idea. And please work with your neighbors, and let's discuss after a minute or so. Oh, by the way, the 152 is basically the hex number 98. So here, that is 152. All right, for the interest of time, let's go through this together, okay? So, hello? Okay, all right. For the interest of time, let's go through this together. First, we load those things to register and blah, blah. These are our, we get it over that. And then let's look at the cycle 0. So this is how the memory looks like right now. And then we will be going to the cycle 1. Basically, these three instructions here. What do you think happens in these three instructions? What's the update in the memory in the cycle 1? Any answers? Basically, you will give me like which what's the value and then which memory address that value goes into, because it's essentially 3 stores here. Any answers? Yes.
Could you say that again? Exactly what you just said.
Wait, what? So yeah. So basically, give me the answer on what's the value being stored, and then what's the address that's being stored at the cycle 1. And then we will do the cycle 2, and then that should pretty much give you an idea of how the loop here works. Any guesses? Any answers? Yes. Sorry, can you say? Oops. But what's the address of that data being stored at in the memory? Remember, like this type of instructions, the 2 is added after the instruction. The address adding 2. Yes.
098, 0x.
Yes, exactly. So the same value will be stored at basically overriding the same address that we loaded from, which is the 098. And what about the second store? What does that do? Okay, I'll give other people a chance. What's the, okay, yeah. So what's the end address is going to be?